Hi everyone, Mr. Markwick here. In today's video, I'm going to continue looking at the idea of feasible regions. In the previous video, we had a bit of an introduction into feasible regions. Now we're just going to introduce some additional constraints. I'm going to refer back to the opening problem where Jason and Kate were running a barbecue at a school fete to raise some money. They were going to sell sausages and steaks. Sausages were 40 cents each and steaks were $1 each. And they had $20 to spend in total. However, the butcher has now said he can only supply sausages at 40 cents and steaks at $1 if they buy at least 10 sausages and at least 6 steaks. So that information now is going to help us create two new constraints, keeping in mind that we already had the constraint of the maximum they could spend is $20, and those two products, the price of the sausage and the price of the steaks, were competing for that resource of $20. Anyway, because we said the number of sausages was represented on the x-axis, so the number of sausages must be at least 10, so therefore x must be greater than or equal to 10, and we said the number of steaks was on the was represented on the y-axis, and the number of steaks must now be greater than or equal to 6, so that y is greater than or equal to 6. So those two new constraints create two new inequalities. X is greater than or equal to 10, y is greater than or equal to 6, and those are added to the Cartesian plane or the graph that we drew in the original problem, which showed a triangular feasible region. We've basically just brought that feasible region in a little bit. Remember the feasible region in that opening problem that we looked at? We just said that you can't buy a negative number of a negative number of steaks or sausages. So we've moved the boundary line in from the y and x axis. So instead of x is equal to 0, y is equal to 0, the boundary line is now x is equal to 10 and y is equal to 6. We still have that, that third constraint or boundary of 0.4x plus y is equal to 20. That's the line there. But remember, anything on those lines, on that boundary of the feasible region or within the area of that feasible region, is a possible or feasible solution to the problem. So any point within there is a feasible solution. So for example, Jason and Kate, if they wanted to, could purchase 20 sausages, so 20 coming off the x-axis, okay, and 10 steaks. So that point there will allow them to purchase a feasible amount of sausages and steaks and still come under the total $20. Okay, so that's what we're going to be looking at today, introducing some additional constraints along with creating, I guess, a third boundary or constraint from the information we get in the problem. So just quickly, I'm also going to point out here that a feasible region is also called or can be called a simplex. So if they're asking you to shade a simplex, they're asking you to shade a feasible region. And each corner point of the simplex where boundary lines meet is called a vertex. Now, vertex or vertices is the plural in feasible regions are really important. So I'll show you what I'm talking about here. Is a vertex there at coordinates 35, 6. Here is another vertex here at 10, 6. And here is another vertex here at 10, 16. So it's a triangle. It has 3 vertices. Those vertices are really important because they often represent optimal solutions, or one of them will anyway. Okay, we'll talk about that later. And to be able to solve for what the values are at those vertices, we use simultaneous equations to solve them. And we've gone through in class already how to solve simultaneous equations using our graphics calculators. And there's a couple ways we can do that, we know. All right. Anyway, vertices are the points where those boundary lines meet, and feasible regions, the green section here, could also be known as a simplex, okay? Now, we're going to get into another example where it says here, Steve buys X pineapples at $2 each and Y watermelons at $3 each. And the additional constraints here, he needs to buy 2 of each, at least 2 of each, and can spend no more than $30. Graph the feasible region for what Steve can buy. So the first thing here, he needs to buy 2 of each. Okay, so he needs to buy at least, 2 of each. So the first thing I'm going to say is, because X is the number of pineapples, that X must be greater than or equal to 2. Y must also be greater than or equal to 2. He must buy at least 2 pineapples and at least 2 watermelons. Now he has $30 to spend in total, so we're going to create a third equation or third inequality based on the information we have here. Now X is the number of pineapples. They're $2 each. So $2 times by X plus $3 times by Y, $3 for each watermelon, is going to be equal to $30. So let's simplify this to 2X plus 3Y is equal to 30. Now remember, he doesn't necessarily have to spend the whole $30, so we will change this to an inequality. 2X plus 3Y is less than or equal to 30. So they are my 3 constraints, I guess, my 3 inequalities. They will become the 3 boundaries of the feasible region or the simplex when we draw it. So I can probably go ahead and put these 2 in. X is greater than or equal to 2. Y is greater than or equal to 2. I'm actually going to put them in as equations. So X is equal to 2 is the first line I'll draw on my Cartesian plane here. So on my Cartesian plane, grab a ruler out. Well, first of all, X is greater than or equal to 2. Let's actually find 2 on the X-axis. There it is there. So I'm actually going to get a ruler now and draw a line along that point. Then I'm also going to look at, in fact, let's use a different color for this, just so that we're not going to get confused. So I might just write that one there in blue. Y is greater than or equal to 2. So on my y-axis, I'm going to find the value 2. There it is. Get my ruler and draw a straight line through 2. This line I'll get it right. This line represents the equation y is equal to 2, which is my boundary line. Sorry, I'm not sure what happened there. Let's get rid of that. Y is equal to 2. And the third line I'm going to draw to create a feasible region is 2x plus 3y is less than or equal to 30. And I'm going to do this one in black. So actually, let me just rewrite that inequality. 2x plus 3y is less than or equal to 30. Now, it's a bit hard. Just trying to draw this a bit harder than just those 2, but it's not that difficult. I can rearrange this to slope-intercept form, and from the y-intercept, then use the slope to help me find a couple of other points and draw a straight line. But all I'm going to do is I'm going to find the 2 intercepts. I'm going to find the x-intercept and the y-intercept using the equation 2x plus 3y is equal to 30. Okay, this equation is basically the same as this inequality. Remember, this is an equation that has an equal sign. This is an inequality because it has an inequality sign. So from that equation, what is my x-intercept? Well, I'm going to substitute in y equals 0, because at any x-intercept, the y value is going to be 0. So I'm just substituting 0 into this equation. So it becomes 2x plus 3 times by 0 is equal to 30. Now, 3 times 0 is just 0. So I'm left with 2x equals 30. To solve that, I'm going to divide by 2 on both sides, which gives me x equals 15, which is this point here. And I'm going to do the same to find my y-intercept, but this time I'm going to substitute in x is equal to 0, because at any y-intercept, the value of x will be 0. So 2 times 0 plus 3y is equal to 30. 2 times 0 is just 0, so I'm left with 3y equals 30. To solve, I'm going to divide by 3 on both sides. Okay, that leaves me with y is equal to 30 divided by 3, which is 10. So that is 10 on my y-axis there. Go ahead, grab my ruler, and put a line or a straight line through those two intercepts as best you can. And that creates a triangle here for me. Remember, this equation is 2x plus 3y is equal to 30. But the inequality for us is, in terms of the problem, the information that we have, 2x plus 3y is less than or equal to 30. So anything underneath that line, above the blue line, and to the right of the red line is our feasible region or our simplex. So I'm going to go ahead and shade that region in. Okay, and that is my feasible region based off the information we have there. X amount of pineapples at $2, Y amount of watermelons at $3 each, and needing to purchase at least 2 pineapples and at least 2 watermelons, and having a total of $30 to spend. Okay, again, you've got your 2 products, pineapples, watermelons, that are competing for the one resource of $30. But now we also have these additional constraints of having to purchase at least a minimum amount of each. Okay, so hopefully that helps, guys. Again, thanks for watching. Look, if you've got any questions, drop them in the comments and I'll do my best to answer. Thanks for watching.